Hello everyone, my name is Ehsan Marjani and I'm glad to have this opportunity to present our work which is event-based RGB sensing with structural light. This work was supervised by Professor Giovanni Beltrame and has been done in the MIST Lab Polytechnique Montreal. Event-based cameras are bio-inspired sensors that report pixel brightness changes. Due to their high dynamic range, pixel bandwidth, temporal resolution, low power consumption, and computational simplicity, they are beneficial for vision-based projects in challenging lighting conditions, and they can detect fast movements with their microsecond response time. However, they only detect changes in light and do not show static or slowly moving objects. Also, the high-resolution versions are monochrome. Because manufacturers usually use color filter arrays on the camera sensor to detect color, which decreases the resolution. We propose to combine the event-based camera with the digital light processing projector. The projector emits rapidly changing RGB patterns of light beams on the object, the reflection of which is captured by the event-based camera. So we can generate full color events from a monochrome event-based camera with no loss of spatial resolution, with the ability to detect static objects, optimize the bandwidth of the camera by detecting the color when and where it is needed, pave the way for frameless RGB-D sensing applications by emitting known patterns. Since the DLP projector has narrowband LEDs, the white balance can be adjusted by changing the current of each LED separately beforehand. As this slide shows, the quality of the color detection of a printed MacBook board increased by doing the white balance correction. To prevent bus saturation, we propose to change the structural light to control the number of events. The proposed ASL method is to control the trade-off between the speed and details. To examine our method, we use different scenarios with static and dynamic objects. We use a color paper pinwheel as the dynamic object. As this slide shows, we are able to reconstruct the color in less than 7 milliseconds, which is equivalent to 150 frames per second. This slide shows the experimental results for the static object. These two rows show that to decrease the color detection error, we need to decrease the coverage percentage, which can be considered as the percentage of details. As expected, by increasing the coverage percentage, we have full image color detection at a lower detection speed. This slide shows that to have a more detailed image, we need to spend more time switching patterns to cover more area. Also, for higher speed scanning, a sparse pattern is needed. Note that a sparse pattern does not decrease the quality of color detection even with higher speed sampling. This slide has been generated by using over 24,000 frames. We released the source code, which also contains the ROS GUI notes for calibration. Thank you for your attention and interest into our work.